Welcome to The Explainer. Today we're going to talk about a massive performance killer in Spark streaming, how you manage huge amounts of state without your jobs just, well, falling over. And we're going to look at a solution that can honestly completely change the game for your data pipelines.
Yeah, if you've ever had one of those long-running Spark streaming jobs, you know the ones. They start to slow down, latency starts spiking all over the place, or they just crash entirely. Well, you've probably run headfirst into the hidden bottleneck of state management. It's an incredibly common and, let's be honest, super frustrating problem.
Okay, so first things first, what do we even mean by stateful processing? Really, it's anytime your application needs to remember something from past events. Think about it. You're counting clicks for each user, or you're joining two real-time streams, or you're trying to spot a pattern over a few minutes. That memory of what happened before, that's the state.
All right, so where does it all go wrong? Well, the root of the problem, it's all about where Spark keeps its state by default. And that's right inside the JVM heap.
You see, by default, Spark just crams all of this state, every single user's click count, all that session data, it crams it right into the executor's JVM memory. And here's the kicker. That means the state is fighting for the exact same very limited memory space that your actual processing tasks need to, do their job.
And as that state just grows and grows, and you've got millions of keys filling up the heap, that's when you trigger the thing that every engineer dreads, the stop the world garbage collection. And it does exactly what it sounds like. It literally freezes your entire application, sometimes for seconds at a time, just to clean up memory.
And this is where the real pain starts. You get these wild, unpredictable latency spikes that just kill your SLAs, those performance promises you make to your users. Then eventually, the state gets too big and bang, your job crashes with an out-of-memory error. And even if it somehow survives, checkpointing is painfully slow because it has to re-upload the entire state every single time.
Okay, so how do we get out of this mess? The answer is actually pretty elegant. We move the state completely off the JVM heap with a super high-performance embedded tool called RocksDB.
All right, this slide really breaks it down. On the left, you've got the old way. Everything's stuck in that JVM heap, fighting for memory, getting hammered by the garbage collector. But then you look on the right with RocksDB, and it's a whole different world. The state moves to its own space in native memory, so the garbage collector just ignores it. It can spill to local disk, so you can handle terabytes of data, and you get these incredibly efficient incremental checkpoints.
So let's look at how this is actually set up. The magic here is that RocksDB isn't some separate server you have to manage. Nope. It embeds itself right inside each Spark executor, acting like a tiny, super fast local database. It keeps all the state right there on the worker, in native memory and on local disk. And then it just efficiently backs up the changes to your durable storage, like S3.
The best way to think about this is imagine trying to build something complex on a tiny, cluttered workbench, where all your tools and all your parts are just in a big pile. That's the JVM heap. Now, RocksDB, that's like having a massive, perfectly organized warehouse right next to your workbench. Your actual workspace stays clean, and you can grab any of the terabytes of tools you need instantly without the clutter.
Okay, but look, this isn't just theory, right? The performance gains that major tech companies are seeing in the real world, they are absolutely dramatic. Take Databricks, for example. They run literally millions of these streaming jobs. And in their benchmarks for these high-throughput pipelines, they saw up to a 4 times reduction in P99 latency. And that P99 latency, that's the one that really matters for your SLAs. That's a huge deal.
But what's really cool about this slide is it tells you why the latency got so much better. Just look at that bottom row. Average garbage collection pauses dropped by a factor of 10. 10 times. By moving the state off heap, they basically eliminated the root cause of the problem, letting the job just run smoothly and predictably.
And look, it's not just Databricks, not by a long shot. This has basically become the industry standard for anyone doing serious streaming at scale. Companies like Adobe, Uber, Apple, they all depend on RocksDB to handle the massive state their real-time systems need.
So when you put RocksDB head-to-head with other options, it just finds that perfect sweet spot. As you can see right here, it gives you the kind of high throughput you'd expect from a fully in-memory solution, but it also gives you the low, stable latency and the durability that you absolutely need for production.
All right, so you're probably thinking, this sounds great, but is it hard to set up?
And the answer is, it's surprisingly simple to turn on. But there are a few key configurations you have to get right to make it stable and ready for production.
And I'm not kidding, getting started is literally this simple. You just set one single configuration property in your Spark app. That's it. That one line tells Spark, hey, stop using that old default memory store and switch over to the much more powerful RocksDB provider.
Okay, but for a real live 24/7 production job, you're going to want to do a bit more. These are the pro tips. First, you absolutely have to set a memory limit so RocksDB doesn't just eat up all the native memory. Second, you definitely want to enable changelog checkpointing. Instead of saving the whole state every time, it only saves the changes. This is a game changer for recovery speed.
So when you put it all together, the stability, the massive scale, the performance boost, it's no surprise at all that RocksDB is now the de facto standard for any serious stateful streaming job on Spark.
So let me leave you with this question. The next time one of your streaming jobs starts to slow down or get unstable, maybe the first question you should ask isn't what's wrong with my code, but is my default state store the hidden bottleneck that's holding my entire pipeline back? The answer could be the key to finally scaling.